In this video, we will cover a problem that has both interference and diffraction built into it. So the problem says a two-slit interference diffraction pattern is observed with a light of wavelength 487 nanometers. And here, the information that is given to us is that, so lambda that's given is equal to 487 nanometer, right? And then the slits have a separation of 0.1 millimeter. So slit separation, that's denoted by D. D is equal to 0.1 millimeter. And the slit width, and it says and a width of A, so that's the slit width, and that's denoted by A. A is an unknown quantity. In fact, the first part of the problem says find the width of A, right? So this is an unknown quantity. So now let's remind ourselves what a two-slit interference diffraction pattern looks like. Well, first of all, what does the diffraction pattern look like? Well, the diffraction pattern, if you remember, it looks like this. It's like a central maximum at theta equals 0, and then minimas at different values of m, and those different values of m refer to the order of the minima. Now here in the problem there's additional information given. It says the third interference maximum is at the same angle as the first diffraction minimum. So the first diffraction minimum refers to these 2 points, right? And if you remember, min for diffraction, right? So min for diffraction, this condition, we wrote it down earlier in a different video. This min diffraction, the condition is A sine theta is equal to m lambda, where m cannot be equal to 0, and we'll call this md because this is a diffraction pattern. Md is not equal to 0, and in fact in this particular problem it says that first diffraction minimum, right? So since it's the first diffraction minimum, that's this condition, so md in this case is equal to 1. Okay, what about interference patterns? When diffraction and interference are formed together, usually the interference pattern is somewhere in the enclosed by this diffraction pattern. So it goes like this on both sides. It's symmetrical on both sides of the stuff. And what it says is that find the width of A if the third interference maximum is at the same angle. So let's go to our interference formulas. So maximum for interference, right? Interference. And maximum for interference, the formula is d sine theta is equal to m interference lambda. Yeah. And here mi can be anything 0, 1, 2, but it's particularly given, it's the third interference maximum, so that tells me that mi has to be equal to 3. Okay. It also says that these two are at the same angle, so the theta value for both of these is the same. So I can work out sine theta from this equation and sine theta from this equation and set them equal to each other. So let's do that. So sine theta is equal to md lambda over A is also equal to mi lambda over d. So now if I just look at the second part of this equation, lambda will fall off, and hence I will find A is equal to d multiplied by md over mi. Right? So this is our answer without numbers. Now if I plug in numbers at this stage, I know that d is given somewhere. D is 0.1 millimeter. So d is 0.1 millimeter multiplied by md, which is, we said that was 1, and mi, which is 3. So this is 1/3 of a 0.1 millimeter. Or this is, one can also write this as d over 3, which is equal to 0.033 millimeter. Right? And that's our answer for D. Okay, so this is part A where this is our answer for A, and so that's the answer for part A. The slit width is a third of 0.1 millimeter. So now part B is asking us to find how many bright fringes, interference fringes, will be seen in the central diffraction maximum. So we have to know what the central diffraction maximum is. Well, the central diffraction maximum forms between the first diffraction minimas. So this is the first diffraction minimum on the left side, and this is the first diffraction minimum on the right side. So in between those two is the diffraction maximum, that's the central diffraction maximum. And the central diffraction maximum is just an envelope curve for the interference fringes that are formed inside. So each of these are going to be bright spots, right? Now we have further information. Going back to part A, it says that the third interference maximum is at the same angle as the first diffraction minimum. So this is where the first diffraction minimum is, and hence the third interference maximum is also over here. But you see, because the diffraction pattern has a zero over here, we will get a zero intensity anyways, which means that the third interference maximum is not seen. The third interference maximum, although it is a maximum, it's really a dark spot because it's also the first diffraction minimum, right? So then, thinking about that, we sometimes we also refer to this as a missing order of interference, right? Missing order. What does missing order mean? It is the order of interference for which the diffraction part of the pattern has a zero of intensity. Because of that, the interference order, although it should have been present, is actually absent. It's not seen. And so when is this happening? This is happening when mi is equal to plus or minus 3, right? This is absent order or missing order, right? So if mi equals plus or minus 3 is absent, then what is present over here within the central maximum, that's got to be anything less than plus or minus 3. And so we'll have mi is equal to 0, plus or minus 1, or plus or minus 2. And these are all present inside central maximum, right? So now we can actually hand count the number of interference fringes there would be. There is 1 for the 0, there are 2 for the plus or minus 1, and then there are 2 for the plus or minus 2. So a total of 5. So we'll see 5 bright fringes. So we'll see 5 bright fringes inside the central diffraction maximum.